There is a boundary out there that most people never think about. Not a wall, not a fence, not any kind of visible line, but a real and measurable place where the influence of our sun gradually gives way to the deeper silence of interstellar space. Tonight, we are going to travel there slowly. We will move outward from the edges of the familiar solar system, through regions of ice and ancient debris, past the reach of the solar wind, and into the vast cold territory that separates our star from the next. Welcome to Sleepy Time Universe, where the biggest questions in science are explored at the pace of a calm and restful night. This is not a journey that requires urgency. The places we are visiting tonight have been there for billions of years, and they will remain long after our instruments have gone quiet. We will look at the Heliosphere and the invisible bubble it creates around our solar system. We will spend time in the Kuiper Belt, a broad ring of frozen worlds beyond the orbit of Neptune. We will consider the scattered disk, where objects follow long elliptical paths far from the Sun, and we will arrive, eventually, at the Oort Cloud, a vast spherical shell of icy bodies so remote that it sits at the very boundary between our solar system and the space between the stars. Tonight, we will journey through each of these regions and explore the edge of what is known. If this sounds like the kind of content you return to, consider subscribing and leaving a comment below. We would love to know. What do you think lies beyond the farthest reach of our solar system? Now let's begin. Chapter 1. The boundary of the solar system. When we talk about the edge of the solar system, we are not talking about a single clean line. There is no moment where space suddenly changes character, no threshold you could cross and know with certainty that you had left one region and entered another. Instead, the solar system fades. It thins out gradually, like the last light of an evening sky giving way to full darkness. The boundaries we use are real, but they are defined by physics rather than by geography, by the behavior of particles and fields, rather than by any visible feature of the landscape. The most commonly cited boundary is the orbit of Neptune, the outermost of the 8 recognized planets. Neptune sits roughly 30 astronomical units from the Sun. 1 astronomical unit is the average distance between the Earth and the Sun, approximately 150 million kilometers. So Neptune orbits at about 4.5 billion kilometers out. That already sounds impossibly remote. But it is, in cosmic terms, still very close to home. The regions we will be exploring tonight extend far beyond Neptune. Hundreds, thousands, and in some cases tens of thousands of astronomical units into space. Another way to think about the solar system's boundary is through the concept of gravitational dominance. The Sun's gravity reaches outward in all directions, holding planets, moons, asteroids, and comets in their orbits. But gravity weakens with distance. At some point, the gravitational pull of other stars begins to compete with the Sun's influence, and the definition of what belongs to our solar system becomes genuinely uncertain. That outer limit is not sharp, and it is not the same in every direction. The solar system is not a perfect sphere. It is shaped by its surroundings, by the movement of the Sun through the galaxy, and by the gravitational presence of neighboring stars. There is also the boundary defined by the solar wind. The Sun constantly releases a stream of charged particles, electrons, protons, and heavier ions that flow outward in all directions at hundreds of kilometers per second. This stream is called the solar wind, and it fills a vast bubble of space around our star. That bubble has a name, the Heliosphere. The outer edge of the Heliosphere marks the point where the solar wind loses its ability to push back against the thin gas of interstellar space. Beyond that edge, the Sun's direct physical influence effectively ends. These different definitions, gravitational, particle-based, orbital, do not all agree on where the solar system ends. And that disagreement is part of what makes this region of space so interesting to study. There is no single answer to the question of where our solar system stops. There are only different ways of asking it, each one revealing something different about the nature of the space we inhabit. For the purposes of tonight's journey, we will work our way outward layer by layer, starting with the heliosphere and moving gradually into more distant territory. Each layer has its own name, its own characteristics, and its own population of objects. Together, they form a picture of a solar system that is far larger, far more complex, and far more active than the familiar image of 8 planets circling a central star. The solar system, it turns out, does not end at Neptune. It extends far into the darkness beyond, and the regions out there are ancient, cold, and full of things we are only beginning to understand. Chapter 2: The Heliosphere and the Solar Wind. The Sun is not a quiet object. At its surface, temperatures reach thousands of degrees, and the processes churning beneath that surface are violent and continuous. Charged particles are constantly being accelerated outward in all directions, escaping the Sun's atmosphere and streaming into space at speeds that range from about 400 to 800 kilometers per second depending on conditions. This continuous outflow is the solar wind, and it has been blowing without interruption for the entire 4.5 billion year history of our solar system. The solar wind is not uniform. It varies in density and speed, depending on the activity level of the Sun. During periods of higher solar activity, the wind is stronger and more turbulent. During quieter periods, it settles into a steadier, more predictable flow. But regardless of these variations, the fundamental character of the solar wind remains the same: a continuous stream of charged particles moving outward from the Sun in every direction, filling the space between the planets and pressing against the boundary of interstellar space. As the solar wind travels outward, it carries with it a magnetic field. The Sun has a powerful magnetic field of its own, and as the solar wind expands into space, it stretches and carries that field along with it. This extended magnetic structure is called the interplanetary magnetic field, and it spirals outward from the Sun in a shape that astronomers sometimes describe as resembling the pattern left by a rotating garden sprinkler. The combination of the solar wind and this magnetic field creates a vast, structured region of space that is fundamentally different in character from the interstellar medium, the thin gas and dust that fills the space between stars. This entire region, the bubble of space dominated by the Sun's wind and magnetic field, is the Heliosphere. It extends outward from the Sun in all directions, though not symmetrically. The side of the Heliosphere facing the direction of the Sun's movement through the galaxy is compressed and relatively blunt. The opposite side, the tail, stretches out much farther into space, shaped by the pressure of the surrounding interstellar medium, much like the wake of a boat moving through water. The exact shape of the Heliosphere has been a subject of ongoing research, and observations from spacecraft and telescopes have gradually refined our understanding of its structure. The Heliosphere serves a crucial function for life on Earth and for the solar system as a whole. It acts as a shield. The interstellar medium is not empty. It contains cosmic rays, which are high-energy particles accelerated by distant supernova explosions and other energetic events across the galaxy. These cosmic rays travel through space at near the speed of light, and without some form of protection, they would reach Earth in much higher numbers than they currently do. The heliosphere deflects and attenuates a significant portion of these incoming particles, reducing the radiation environment inside the solar system to levels that are far more hospitable to life. The scale of the heliosphere is difficult to hold in mind. At its widest, it extends to roughly 100 astronomical units or more in the direction of the heliospheric nose, the compressed leading edge, and considerably farther in the direction of the tail. For context, the distance from the Earth to the Sun is 1 astronomical unit. The heliosphere, at its widest, is at least 100 times that distance across. Neptune, the outermost planet, orbits at 30 astronomical units, well inside the heliosphere's outer boundary. Within the heliosphere, the solar wind flows outward with relatively little resistance. The planets, their moons, and the various smaller bodies of the solar system all sit inside this bubble, bathed in the continuous stream of particles and fields that the Sun produces. It is, in a very real sense, the Sun's atmosphere, an atmosphere so large that it contains everything we have ever directly explored, and extends far beyond into regions that only a handful of spacecraft have ever reached. Understanding the heliosphere is essential to understanding what lies beyond it. The boundary of the heliosphere is not a wall so much as a transition zone, a place where the outward pressure of the solar wind finally meets the inward pressure of the interstellar medium, and the two reach a kind of equilibrium. That transition happens in stages, and the first of those stages has a name of its own. Chapter 3. The Termination Shock. As the solar wind streams outward from the Sun, it travels at supersonic speeds. This is not supersonic in the familiar sense of faster than the speed of sound through air. In space, the relevant comparison is the speed of magnetosonic waves, which are the equivalent of sound waves in a magnetized plasma. By that measure, the solar wind moving at hundreds of kilometers per second is indeed supersonic, and it remains so for an enormous distance from the Sun. But at a certain point, something changes. The solar wind begins to feel the resistance of the interstellar medium pressing inward, and it can no longer maintain its speed. It slows down abruptly, and in slowing down, it becomes denser, hotter, and more turbulent. The place where this transition happens is called the termination shock. A shock in physics has a specific meaning. It is a boundary where a fast-moving fluid, in this case the solar wind plasma, transitions almost instantaneously from supersonic to subsonic flow. The change is not gradual. It happens across a very thin region of space, and on either side of that region the conditions are dramatically different. Ahead of the termination shock, moving outward from the Sun, the solar wind is fast, thin, and cool. Behind it, on the far side from the Sun, the wind has slowed, compressed, and heated. The termination shock is, in a sense, the solar wind's first encounter with the wider universe beyond our star's immediate domain. The termination shock was a theoretical prediction for many decades before it was directly observed. Scientists knew it had to exist somewhere, but pinpointing its location required a spacecraft capable of traveling far enough from the Sun to cross it. That spacecraft was Voyager 1. Launched in 1977, Voyager 1 spent decades traveling outward through the solar system, passing Jupiter and Saturn before heading into the outer reaches of the heliosphere. In 2004, at a distance of roughly 94 astronomical units from the Sun, Voyager 1 crossed the termination shock and sent back data confirming what models had predicted. The solar wind on the far side of the boundary was slower, denser, and hotter, exactly as expected. Voyager 2, traveling in a different direction, crossed the Termination Shock in 2007 at a distance of approximately 84 astronomical units. The fact that the two spacecraft crossed at different distances confirmed something that scientists had suspected. The Termination Shock is not a perfectly symmetrical sphere around the Sun. Its distance from the Sun varies depending on direction, influenced by the pressure of the local interstellar medium and by variations in the solar wind itself. In the direction Voyager 2 was traveling, the boundary was closer to the Sun than where Voyager 1 had crossed. The heliosphere, like so many structures in space, is asymmetrical. Beyond the Termination Shock lies a region called the heliosheath. This is the zone between the Termination Shock and the next major boundary, the Heliopause. In the heliosheath, the solar wind continues to move outward, but it does so slowly and chaotically. It has lost its supersonic character and become a turbulent, compressed plasma. The heliosheath is thought to be tens of astronomical units thick, making it one of the largest distinct regions in the outer solar system. Both Voyager spacecraft spent years traveling through the heliosheath after crossing the Termination Shock, sending back measurements of its magnetic field, particle density, and temperature. The data returned from the heliosheath was surprising in several ways. The magnetic field behaved differently than models had predicted. The distribution of energetic particles was not what scientists expected. These discrepancies have driven ongoing refinements to our models of the heliosphere, and they serve as a reminder that even our nearest cosmic neighborhood contains phenomena that are not yet fully understood. The outer solar system is not a simple place, and the boundary regions of the heliosphere are among the most complex environments that any spacecraft has ever passed through. The Termination Shock, then, is the first threshold, the point where the solar wind announces that it has reached its limits and begins its slow, turbulent decline. Beyond it, the heliosheath stretches outward toward the final boundary of the Sun's direct influence, a boundary that marks the true edge of the solar wind's reach. Chapter 4. The Heliopause, where the Sun's reach ends. Beyond the heliosheath, after the solar wind has slowed and churned its way through tens of astronomical units of turbulent plasma, there is one final boundary. It is the place where the solar wind stops altogether, where the outward pressure of everything the Sun has been pushing into space for billions of years finally equals the inward pressure of the interstellar medium, and the two come to a standstill. This boundary is called the Heliopause, and it represents, in the most physical sense we have, the outer edge of the Sun's direct influence on the space around it. The Heliopause is not a solid surface. It has no texture, no color, no feature that a passing traveler could point to and say, "There, that is the line." It is a boundary defined entirely by pressure. On one side, the solar wind. On the other, the interstellar medium, the thin, cold gas and dust that drifts between the stars of our galaxy. The two meet at the heliopause and push against each other in a kind of permanent equilibrium. Neither advances significantly, neither retreats. The boundary holds, maintained by the ongoing balance of forces from either side. Voyager 1 crossed the heliopause in 2012 at a distance of approximately 121 astronomical units from the Sun. It was a moment that scientists had anticipated for decades, and the confirmation came not from a single dramatic reading, but from a gradual accumulation of data pointing in the same direction. The density of particles around the spacecraft changed. The magnetic field shifted. The population of cosmic rays, those high-energy particles from outside the solar system, increased sharply, no longer held back by the heliosphere's protective influence. Taken together, these changes indicated that Voyager 1 had passed through the heliopause and entered interstellar space. It became the first human-made object to do so. Voyager 2 followed in 2018, crossing the heliopause at roughly 119 astronomical units. Its crossing provided something that Voyager 1's could not: a second data point from a different direction, allowing scientists to compare conditions at the heliopause from two separate locations. The data from Voyager 2 confirmed the general picture established by Voyager 1, but also revealed differences. The temperature and density of the plasma at the boundary were not identical in both directions. The heliopause, like the termination shock before it, is not a uniform sphere. It is shaped by the asymmetries of the Sun's environment, by the direction of the Sun's motion through the galaxy, and by variations in the density of the surrounding interstellar medium. One of the most significant findings from both Voyager crossings was the behavior of the magnetic field at the heliopause. Scientists had expected the solar magnetic field to rotate and align with the interstellar magnetic field at the boundary. Instead, the transition was more abrupt than predicted, and the interstellar magnetic field had a direction and strength that surprised researchers. These findings have contributed to ongoing debates about the precise structure and shape of the heliosphere, and have prompted new models of how the Sun interacts with its galactic environment. Beyond the heliopause, the interstellar medium begins. The particles out there are not from the Sun. The magnetic field is not the Sun's. The space between Voyager 1 and the nearest star is filled with material that belongs to the galaxy itself. Ancient gas and dust that has drifted through interstellar space for timescales far longer than our solar system has existed. In this region, the Sun is just one star among hundreds of billions, its light and wind indistinguishable at sufficient distance from the contributions of all the others. And yet, the Sun's gravitational influence does not end at the heliopause. Gravity reaches much farther than the solar wind. Objects can orbit the Sun at distances far beyond 120 astronomical units, held in place not by the solar wind but by gravity alone. The heliopause marks the end of the Sun's physical reach in terms of particles and fields, but the gravitational domain of the solar system extends much farther out, into the cold, dark regions we will be exploring in the chapters ahead. The heliopause is an ending and a beginning. It is where the Sun's breath stops, but where the Sun's gravity still holds sway over a vast and largely unexplored territory of ice, rock, and ancient material stretching far into the darkness beyond. Chapter 5. The Kuiper Belt. Step back from the heliopause for a moment and return to a region much closer to home, though still far beyond anything most people picture when they think of the solar system. Beginning just beyond the orbit of Neptune, at around 30 astronomical units from the Sun, and extending outward to perhaps 50 astronomical units, lies a broad, flat region of space populated by hundreds of thousands of icy objects. Some are small, no more than a few kilometers across. Others are large enough to be considered dwarf planets. Together, they form one of the most significant structural features of the outer solar system. This region is called the Kuiper Belt, and it has fundamentally changed the way astronomers think about the architecture of our solar system. The Kuiper Belt was predicted before it was observed. In the mid-20th century, astronomers began to suspect that the region beyond Neptune was not simply empty space. The existence of short-period comets, those that complete their orbits in less than 200 years, suggested there had to be a reservoir of icy bodies somewhere in the outer solar system from which these comets were being drawn. A comet that visits the inner solar system loses material with every pass near the Sun, and over time it diminishes. If short-period comets had been doing this since the beginning of the solar system, they would all have been exhausted long ago, unless new ones were continuously being supplied from some nearby source. The Kuiper Belt was the answer to that question. The belt is named after the Dutch-American astronomer Gerard Kuiper, who in 1951 published a paper discussing the possibility of a disk of icy debris beyond Neptune. It is worth noting that the Irish astronomer Kenneth Edgeworth had proposed something similar a few years earlier, in 1943, which is why the region is sometimes referred to as the Edgeworth-Kuiper Belt. In either case, the prediction was made decades before the technology existed to confirm it. The first Kuiper Belt object beyond Pluto was not discovered until 1992, when astronomers David Jewett and Jane Liu detected a small faint body, designated 1992 QB1, using a telescope in Hawaii. That discovery opened a new chapter in planetary science. Since 1992, thousands of Kuiper Belt objects have been catalogued. They range enormously in size and composition, though most share certain broad characteristics. They are cold, having spent their entire existence far from the sun's warmth. They are icy, composed of mixtures of frozen water, methane and ammonia, alongside rocky and dusty material. And they are old, remnants of the material that formed the outer solar system more than 4 billion years ago, preserved in the deep cold of space with relatively little alteration since the time of their formation. The Kuiper Belt is sometimes compared to the asteroid belt that lies between Mars and Jupiter, but the comparison only goes so far. The Kuiper Belt is far larger. It occupies a much greater volume of space and contains considerably more mass than the asteroid belt. Its objects are also compositionally different, being rich in ices rather than the silicate and metallic materials that dominate the asteroid belt. And while the asteroid belt is largely a zone of rocky debris shaped by Jupiter's gravity, the Kuiper Belt structure has been influenced by Neptune, whose gravitational resonances have organized many Kuiper Belt objects into specific orbital patterns. Some Kuiper Belt objects are locked into what are called orbital resonances with Neptune, relationships where the orbital period of the object and the orbital period of Neptune form a simple numerical ratio. Pluto, for example, completes 2 orbits around the Sun for every 3 that Neptune completes. This 3-to-2 resonance is shared by a large population of Kuiper Belt objects known as Plutinos, named after Pluto. These resonances are not coincidental. They are the result of gravitational interactions over billions of years that have gradually herded objects into stable configurations, preventing them from being ejected from the solar system or drawn into Neptune's path. The Kuiper Belt is a place of ancient stillness. The objects out there move slowly through space, following their long orbits in perpetual cold and darkness. Occasionally, gravitational interactions nudge one of them onto a new path, perhaps inward toward the Sun, where it will brighten into a comet visible from Earth, or outward into even more remote regions of the solar system. But for the most part, the Kuiper Belt is a stable relic, a record of conditions in the outer solar system from the very earliest period of its formation, preserved for billions of years in the cold beyond Neptune. Chapter 6. Worlds of the Kuiper Belt, Pluto and beyond. When most people think of Pluto, they think of a demotion. In 2006, the International Astronomical Union redefined the criteria for planethood, and Pluto, which had been considered the ninth planet since its discovery in 1930, was reclassified as a dwarf planet. The decision was controversial at the time and remains a topic of debate in some circles. But setting aside the question of classification, what the reclassification really represented was a shift in understanding, a recognition that Pluto was not an isolated oddity at the edge of the solar system, but rather the largest and most prominent member of a vast population of similar objects. Pluto was not demoted so much as it was placed in its proper context. Pluto was discovered in 1930 by the American astronomer Clyde Tombaugh, who was systematically photographing the sky in search of a predicted ninth planet. For decades, it was studied only as a point of light, its surface and atmosphere beyond the reach of any telescope then in existence. That changed dramatically in July 2015, when NASA's New Horizons spacecraft made its historic flyby of the Pluto system, returning the first detailed images of Pluto and its largest moon, Charon. What those images revealed was astonishing. Pluto was not a simple, cratered ball of ice. It was a geologically complex world with mountain ranges, vast plains of nitrogen ice, a thin but distinct atmosphere, and surface features that suggested ongoing or relatively recent geological activity. The most striking feature visible in the New Horizons images was a large, heart-shaped region of pale nitrogen ice, now informally known as Tombaugh Regio, named in honor of the astronomer who discovered Pluto. Within this region lies a smooth, crater-free plain called Sputnik Planitia, which is thought to be geologically young, perhaps no more than a few tens of millions of years old. The absence of craters suggests that the surface there has been renewed relatively recently, possibly through a process of convection in which slowly churning cells of nitrogen ice resurface the plain over time. The idea that a world so far from the Sun, receiving so little energy, could maintain any kind of geological activity was unexpected and has prompted significant scientific discussion. Charon, Pluto's largest moon, is itself a remarkable object. It is so large relative to Pluto, about half its diameter, that the two are sometimes described as a double dwarf planet system rather than a planet and its moon. The center of mass around which they orbit lies outside Pluto's surface, meaning they orbit each other in a gravitational dance, rather than one simply circling the other. Charon's surface is quite different from Pluto's, darker and dominated by water ice rather than nitrogen ice, with its own set of canyons, cliffs, and a large dark reddish region near its north pole that scientists believe may be formed from complex organic molecules created when methane escaping from Pluto's atmosphere is captured by Charon's gravity and processed by radiation. Beyond Pluto, the Kuiper Belt contains a growing catalogue of similarly fascinating worlds. Eris, discovered in 2005, is slightly smaller in volume than Pluto, but more massive, and its discovery was one of the key factors that prompted the redefinition of planetary criteria. Makemake and Haumea are two other recognized dwarf planets in the Kuiper Belt, each with its own distinctive characteristics. Haumea is particularly unusual. It rotates so rapidly that it has been flattened into an elongated shape, more like a rugby ball than a sphere, and it has a faint ring system, making it one of only a small number of objects in the outer solar system known to possess rings. Many more large Kuiper Belt objects likely remain undiscovered. The region is vast, and the objects within it are faint and slow-moving, making them difficult to detect even with modern telescopes. Estimates suggest there could be hundreds of objects in the Kuiper Belt, large enough to be classified as dwarf planets if they were ever observed in sufficient detail. Each one represents a preserved sample of the early solar system, a world shaped by the conditions that existed billions of years ago when the planets were still forming. The worlds of the Kuiper Belt are, in their own quiet way, among the most scientifically valuable objects in the solar system. They have not been heated, melted, or geologically reworked to the degree that the inner planets have. They sit in cold storage, holding within their ice and rock a record of composition and structure that speaks directly to the conditions of the early solar system. Studying them is, in a very real sense, a form of archaeology, sifting through the oldest preserved material in our cosmic neighborhood in search of clues about where we came from. Chapter 7. The Scattered Disk. Not all of the objects beyond Neptune follow the relatively orderly paths of the Kuiper Belt. There is another population out there, one whose members travel on orbits that are far more elongated, far more tilted, and far more unpredictable. These objects spend part of their time in the region of the Kuiper Belt, but venture much farther out on the distant leg of their journeys, swinging away from the Sun to distances of hundreds of astronomical units before slowly returning. This population occupies a region called the scattered disk, and it represents one of the most dynamically active zones in the outer solar system. The scattered disk overlaps with the outer Kuiper Belt in its innermost regions, but extends much farther out. Its inner edge sits at roughly 30 to 35 astronomical units, near Neptune's orbit, while its outer boundary fades gradually into the more remote reaches of the solar system, eventually blending into the territory associated with the Oort Cloud. The objects within it are called scattered disk objects, and they are defined not so much by where they are at any given moment, but by the character of their orbits. Highly elliptical paths that bring them close to Neptune at their nearest point and carry them far into the outer solar system at their farthest. The name scattered disk refers to the process by which these objects ended up on such unusual orbits. They were scattered, gravitationally deflected by Neptune during the early history of the solar system. In the chaotic period following the formation of the planets, Neptune's orbit was not fixed in its current position. Models of solar system formation suggest that the giant planets migrated significantly during the first few 100 million years, and as Neptune moved outward, it encountered a vast population of icy bodies in the outer solar system. Many of these objects were flung onto new trajectories by close gravitational encounters with the planet. Some were ejected from the solar system entirely. Others were scattered into the highly elongated orbits that define the scattered disk today. The most well-known object in the scattered disk is Eris, the dwarf planet, whose discovery in 2005 triggered the reclassification of Pluto. Eris follows an orbit that takes it from about 38 astronomical units at its closest approach to the Sun, out to nearly 97 astronomical units at its farthest. Its orbital period is approximately 559 years, meaning it completes one full orbit in a span of time longer than recorded human history. Despite its remote and elongated path, Eris is a substantial world, dense, rocky, and covered in a bright layer of methane frost that makes it one of the most reflective objects in the solar system. Another significant scattered disk object is Sedna, discovered in 2003. Sedna is unusual even by scattered disk standards. Its orbit is extraordinarily elongated, taking it from about 76 astronomical units at its closest point to the Sun, out to roughly 937 astronomical units at its farthest. Its orbital period is estimated at around 11,000 years. At its most distant, Sedna ventures into territory that begins to approach the inner edge of the Oort Cloud, making it something of a bridge object between the scattered disk and the more remote regions of the solar system. Some astronomers have proposed that Sedna's unusual orbit may have been shaped not just by Neptune, but by the gravitational influence of a distant, as yet undiscovered large planet, a hypothesis that remains unconfirmed but continues to attract serious scientific attention. The scattered disk is also considered the primary source of a class of objects known as centaurs, small icy bodies that orbit the Sun in the region between Jupiter and Neptune. Centaurs are thought to be scattered disk objects that have been nudged inward by gravitational interactions, placing them on unstable orbits that cross the paths of one or more of the giant planets. Their orbits are inherently temporary on astronomical timescales. Eventually, they will be ejected from the solar system, sent into the inner solar system, to become short-period comets, or collide with a planet or the Sun. They are transient visitors to the middle solar system, passing through on journeys that began in the outer reaches and will end in one of several possible fates. The scattered disk as a whole is a region of ongoing dynamical evolution. Unlike the relatively stable Kuiper Belt, where many objects have settled into predictable resonant orbits, the scattered disk is a place of gradual change. Gravitational interactions continue to nudge objects onto new paths over millions and billions of years. Some are slowly pushed outward into the Oort Cloud. Others drift inward toward the planetary region. The scattered disk is, in this sense, a bridge, a transitional zone between the comparatively ordered architecture of the Kuiper Belt and the vast, remote territory that lies beyond. Chapter 8. Long-period comets and where they come from. On rare occasions, something extraordinary happens in the night sky. A comet appears that was not there before, a faint smudge of light that grows brighter over weeks and months as it falls toward the Sun, developing a tail of gas and dust that can stretch across a significant portion of the sky. These are not the short-period comets that return on predictable schedules, completing their orbits in decades or centuries. These are long-period comets, objects making their first and often only visit to the inner solar system, arriving from distances so vast that their journeys to reach us have taken thousands or even millions of years. Long-period comets are defined by their orbital periods. They take more than 200 years to complete a single orbit around the Sun, and many take far longer than that. Some have orbital periods measured in the tens of thousands of years. Others appear to be on trajectories that are only barely bound to the Sun's gravity, meaning they will make one pass through the inner solar system and then continue outward into interstellar space, never to return. When astronomers calculate the original orbits of these comets, tracing their paths back before the gravitational influence of the planets altered their trajectories, they find something remarkable. Nearly all long-period comets appear to originate from an enormous distance, somewhere between 10,000 and 100,000 astronomical units from the Sun. This observation was the key piece of evidence that led the Dutch astronomer Jan Oort to propose, in 1950, the existence of a vast reservoir of icy bodies surrounding the solar system at enormous distances. Oort noticed that long-period comets seemed to arrive from all directions in the sky, not just from the plane of the solar system where the planets orbit, but from above and below as well, distributed roughly equally across the entire celestial sphere. This isotropic distribution, as it is called, was difficult to explain if the comets were coming from a flattened disk like the Kuiper Belt. It strongly suggested instead a roughly spherical source. a shell of material surrounding the solar system on all sides. Oort also noticed that the distribution of original orbital energies for long-period comets showed a distinct clustering. A large number of them appeared to be coming from very similar distances, in a range corresponding to roughly 20,000 to 100,000 astronomical units. This clustering suggested that there was something out there at those distances, a real physical population of objects from which these comets were being drawn, not just a mathematical abstraction. The structure Oort proposed to explain these observations became known as the Oort Cloud, and while no spacecraft has ever visited it, and no telescope has ever directly imaged an object within it, the evidence for its existence accumulated from long-period comet statistics remains compelling. The mechanism by which comets are sent from the Oort Cloud into the inner solar system is an important part of the story. Objects in the Oort Cloud do not spontaneously decide to fall inward. They are nudged. The most significant nudging force comes from the gravitational influence of passing stars. As the Sun moves through the galaxy over millions of years, other stars occasionally pass within a few light years of our solar system. Their gravity, though weak at such distances, is sufficient to perturb the orbits of objects in the distant Oort Cloud, changing their trajectories slightly. For most objects, these perturbations are minor and result in no dramatic change. But for some, the perturbation is just enough to send them onto a path that brings them significantly closer to the Sun. The galactic tide is another important factor. The Milky Way itself exerts a gravitational influence on the outer solar system, a slowly varying tidal force produced by the combined mass of all the stars, gas, and dark matter in the galaxy. This galactic tide gently stirs the orbits of Oort Cloud objects over long timescales, gradually shifting the orientations of their orbital planes and occasionally directing objects inward. The galactic tide and stellar perturbations work together, sometimes reinforcing each other, to maintain a slow but steady trickle of comets falling into the inner solar system from the reservoir of the Oort Cloud. When a long-period comet finally arrives in the inner solar system after its immense journey, it is encountering conditions it has never experienced before. The warmth of the Sun begins to heat its surface, causing frozen ices to sublimate, to transform directly from solid to gas without passing through a liquid phase. This outgassing carries dust and other material away from the comet's nucleus, forming the coma, a fuzzy envelope of gas and dust that surrounds the solid core. The solar, wind and radiation pressure then push this material away from the Sun, creating the comet's tail, always pointing away from the Sun regardless of the direction the comet is traveling. Each pass near the Sun costs the comet material. The ices that have been preserved for billions of years in the cold of the Oort Cloud are lost in a matter of months as the comet swings through the inner solar system. For many long-period comets, this first visit is also their last. They exhaust a significant portion of their volatile material, and if they survive the passage without breaking apart, they continue outward on an orbit that may take them back to the distant reaches of the solar system, or may carry them entirely out of it. Either way, the comet that returns is not quite the same object that arrived. The ancient ice that once held the record of the early solar system's chemistry has been lost to space, scattered as gas and dust across the void. Chapter 9. The Oort Cloud. We have arrived at the most remote region of the solar system that we can speak about with any real confidence. A place so distant and so vast that it defies easy description, and yet one whose existence is supported by careful observation and decades of theoretical work. The Oort Cloud is not a place that any spacecraft has visited. It is not a place that any telescope has directly imaged. It is, in the most honest sense, an inference, a structure whose presence we deduce from the behavior of the comets that occasionally fall inward from it, much the way you might infer the existence of a forest you cannot see by watching the birds that emerge from it. Jan Oort's 1950 paper was a landmark in the history of planetary science. Working from a dataset of long-period comet orbits, Oort recognized patterns that pointed toward a common origin at enormous distances from the Sun. His proposal was elegant in its simplicity, that surrounding the solar system, at distances ranging from perhaps a few thousand to as many as 100,000 astronomical units, there exists a vast spherical reservoir of icy bodies left over from the formation of the solar system. These objects, he argued, spend most of their existence in cold, undisturbed orbits, occasionally perturbed by passing stars or the gravitational tide of the galaxy into paths that bring them falling inward toward the Sun. The Oort Cloud is thought to have two broad components. The inner Oort Cloud, sometimes called the Hills Cloud, after the astronomer Jack Hills, who proposed its existence in 1981, is a denser, more flattened region that begins at roughly 2,000 astronomical units from the Sun and extends to perhaps 20,000 astronomical units. It is believed to contain a large population of objects that are more tightly bound to the Sun's gravity and less susceptible to perturbation by passing stars. The outer Oort Cloud, which is the region Oort originally described, extends from around 20,000 astronomical units out to perhaps 100,000 astronomical units or more. It is this outer region that is roughly spherical in shape, explaining why long-period comets arrive from all directions rather than from the plane of the solar system alone. The total number of objects in the Oort Cloud is genuinely staggering to consider. Estimates based on comet flux and theoretical models suggest that the outer Oort Cloud alone may contain several trillion icy bodies, objects ranging from small, kilometer-sized chunks of ice and rock up to bodies comparable in size to the larger Kuiper Belt objects. The inner Oort Cloud may contain even more. The combined mass of all these objects is uncertain, but estimates typically place it at somewhere between a few times the mass of the Earth and perhaps 5 or 10 Earth masses. It is, in terms of sheer number of objects, by far the most populous region of the solar system. Despite containing trillions of objects, the Oort Cloud is extraordinarily empty. The volume of space it occupies is so immense that even with trillions of bodies distributed throughout it, the average distance between any two objects is enormous. If you were somehow placed at a random location within the Oort Cloud, the chances of being close to any individual object would be vanishingly small. The Oort Cloud is not a crowded place. It is a thin, ghostly halo of material spread across an almost incomprehensibly large volume of space, its population invisible to us not because there is nothing there, but because the objects are too faint, too cold, and too remote for any instrument we currently possess to detect directly. The composition of Oort Cloud objects is thought to resemble that of long-period comets, which serve as our primary source of information about the cloud's contents. These comets are rich in water ice, carbon monoxide, carbon dioxide, methane, and ammonia, along with silicate dust and complex organic molecules. Some of the organic compounds found in comets are of considerable scientific interest. They include molecules that are relevant to the chemistry of life, raising questions about the role that cometary material may have played in delivering organic compounds to the early Earth. The Oort Cloud, as the reservoir from which these comets come, is therefore connected in an indirect but meaningful way to questions about the origin of life in our solar system. The Oort Cloud also occupies an unusual position in terms of the Sun's gravitational domain. At its outer edges, the Sun's gravitational hold on individual objects is extremely weak, so weak that the gravitational influence of nearby stars and the galactic tide can compete with it. Objects at the outermost reaches of the Oort Cloud exist in a gravitational environment that is genuinely shared between our solar system and the broader galaxy. They are barely bound to the Sun, drifting in orbits so large and so slow that a single orbit takes millions of years to complete. In a very real sense, the outermost Oort Cloud objects exist at the boundary between our solar system and the rest of the Milky Way. Chapter 10. The Scale of the Oort Cloud. There is a particular challenge that comes with trying to understand the Oort Cloud, and it is not a scientific one. The science, while complex, is manageable. The challenge is one of scale. The distances involved in describing the Oort Cloud are so far beyond ordinary human experience that the numbers, stated plainly, tend to pass through the mind without leaving much impression. 100,000 astronomical units, a light year, 2 light years. These are not phrases that carry intuitive weight. They require a kind of deliberate mental effort to appreciate, and even then, the appreciation is always incomplete. Tonight, rather than simply stating the numbers, we will try to build a sense of the scale gradually, moving outward from familiar distances until we arrive at something approaching a genuine feeling for how large the Oort Cloud actually is. Begin with the Earth and the Moon. The average distance between them is about 384,000 kilometers. It is a distance that human beings have actually traveled. 12 people walked on the Moon between 1969 and 1972, and the journey took roughly 3 days each way. It is the only significant cosmic distance that has a direct human reference point. Now multiply that distance by about 400. That gives you the distance from the Earth to the Sun. 1 astronomical unit, approximately 150 million kilometers. The Sun is 400 times farther from Earth than the Moon is. Now move outward to Neptune. At 30 astronomical units, Neptune is 30 times farther from the Sun than the Earth is. Light, traveling at 300,000 kilometers per second, takes about 8 minutes to travel from the Sun to the Earth. It takes roughly 4 hours to travel from the Sun to Neptune. A spacecraft traveling at the speed of Voyager 2, approximately 15 kilometers per second, would take about 12 years to reach Neptune from Earth, which is roughly how long it actually took after Voyager 2's launch in 1977. The termination shock, where the solar wind begins to slow, lies at roughly 80 to 100 astronomical units. That is 3 times farther out than Neptune. The Heliopause, where the solar wind stops entirely, sits at around 120 astronomical units. Light takes about 16 to 17 hours to travel from the Sun to the Heliopause. These distances are already difficult to picture, but they are still within the range of what our spacecraft have actually reached. Voyager 1, the most distant human-made object, has been traveling for nearly 5 decades and is now well beyond the Heliopause. But it has barely begun to approach the Oort Cloud. The inner edge of the Oort Cloud is thought to begin at roughly 2,000 astronomical units from the Sun. At Voyager 1's current speed, reaching that distance would take approximately another 300 years from now. The outer edge of the Oort Cloud extends to perhaps 100,000 astronomical units. Reaching that distance at Voyager speed would take roughly 30,000 years. These are not numbers that describe a journey any human civilization has ever contemplated in practical terms. They describe a structure so remote that even our fastest spacecraft, launched nearly 50 years ago and still operating, has covered only a small fraction of the distance required to reach it. It helps to shift from astronomical units to light travel time. Light takes about 8 minutes to reach Earth from the Sun. It takes about 16 hours to reach the Heliopause. It takes weeks to reach the inner edge of the Oort Cloud. And it takes over a year, more than a year of traveling at the speed of light, to reach the outer edge of the Oort Cloud. The nearest star to our Sun, Proxima Centauri, is about 4¼ light years away. The outer Oort Cloud extends to perhaps 1 or 2 light years from the Sun. This means the Oort Cloud reaches roughly a quarter to halfway to the nearest star. Our solar system, in its fullest extent, is not a small dot in the galaxy. It is an enormous structure that occupies a significant volume of the space between the stars. One further comparison helps to anchor this. If you were to shrink the entire solar system from the Sun out to the Heliopause to the size of a single sheet of paper, the Oort Cloud on that same scale would extend outward to a distance of roughly 100 meters in every direction. The familiar solar system, with all its planets and moons and asteroid belts, would be a single page. The Oort Cloud would be the size of a city block surrounding that page on all sides. And beyond the Oort Cloud, the nearest star would be several kilometers away on the same scale. The gulf between stars, even accounting for the enormous reach of the Oort Cloud, is almost entirely empty. This is the scale within which we exist. The solar system we know, the one with 8 planets and a sun at the center, is a small, warm, bright kernel at the heart of a vast and ancient structure that reaches nearly to the stars. The Oort Cloud is the true extent of our solar system, and it dwarfs everything within it. Chapter 11. How the Oort Cloud formed. Understanding. What the Oort Cloud is leads naturally to the question of how it came to be. A spherical shell of trillions of icy objects surrounding the solar system at distances of thousands to hundreds of thousands of astronomical units does not arrange itself without cause. The Oort Cloud has a history, and that history reaches back to the earliest period of the solar system's existence, to a time when the planets were still forming, and the region around the young sun was a chaotic, crowded place very different from the relatively orderly system we inhabit today. The leading explanation for the Oort Cloud's formation begins in the region of the giant planets. In the early solar system, the zone where Jupiter, Saturn, Uranus, and Neptune were forming was populated by an enormous number of smaller icy and rocky bodies, the planetesimals from which the planets themselves were built. Not all of these planetesimals were incorporated into planets. Many remained as free-floating objects in the outer solar system, and as the giant planets grew in size and gravitational influence, they began to interact with these smaller bodies in increasingly powerful ways. The process was one of gravitational scattering. As a small icy body passed close to one of the giant planets, the planet's gravity would alter its trajectory. Depending on the geometry of the encounter, the body might be flung inward toward the sun, sent into a different orbit within the planetary region, or hurled outward to great distances. Jupiter, the most massive planet, was particularly effective at ejecting objects entirely from the solar system, sending them onto hyperbolic trajectories from which they would never return. The less massive outer planets, particularly Uranus and Neptune, were more likely to scatter objects outward onto highly elongated orbits rather than ejecting them completely. It was this outward scattering by Uranus and Neptune that is thought to have populated the Oort Cloud. Objects flung outward by these planets entered orbits with very large aphelion distances. the farthest points of their orbits, reaching out to thousands or tens of thousands of astronomical units from the Sun. Initially, these orbits were still highly elongated, bringing the objects back close to the planetary region at their nearest approach. But over time, additional forces began to reshape these orbits in a crucial way. This is where the influence of the early galactic environment becomes important. In the first billion years of the solar system's existence, the Sun was almost certainly located in or near the star cluster in which it formed. Star clusters are dense environments, and the gravitational influence of nearby stars would have been considerably stronger than it is today, when the Sun has long since drifted away from its birth cluster into a more isolated region of the galaxy. The combined gravitational effect of these nearby stars, along with the galactic tide, acted on the highly elongated orbits of the scattered objects and gradually lifted their perihelia, their closest approach points to the Sun, away from the planetary region. This lifting of the perihelion is the key step in Oort Cloud formation. An object that has been scattered outward by Neptune still returns to the inner solar system at its closest approach, where it can be scattered again or eventually ejected. But if something lifts the perihelion of its orbit, moves the closest approach point outward, away from Neptune's reach, the object becomes effectively decoupled from the planetary region. It can no longer be scattered further by the giant planets. Its orbit stabilizes at large distances from the Sun, and it becomes a permanent resident of the outer solar system. Over billions of years, this process gradually accumulated a vast population of objects in the region we now call the Oort Cloud. The early stellar environment was not the only contributor to this process. The galactic tide, which we encountered in the previous chapter as a mechanism for sending comets inward from the Oort Cloud, also played a role in building it. By slowly modifying the orientations and shapes of orbits over long timescales, the galactic tide helped to circularize and stabilize orbits at large distances, contributing to the roughly spherical shape of the outer Oort Cloud. The fact that the Oort Cloud is spherical rather than disk-shaped, unlike the Kuiper Belt and the scattered disk, is itself a signature of the isotropic nature of the galactic tide and stellar perturbations, which act from all directions rather than preferentially in the plane of the solar system. There is an additional layer to the story of the Oort Cloud's formation that has gained attention in recent decades. Some models suggest that a significant fraction of the Oort Cloud's population may not have originated in our own solar system at all. During the period when the Sun was still part of its birth cluster, the member stars of that cluster were close enough to each other that objects could potentially be exchanged between their respective outer solar systems. A body scattered outward by a planet in a neighboring young star system might have been captured by the Sun's gravity and incorporated into what would become our Oort Cloud. If this is correct, the Oort Cloud may be a composite structure, partly built from material native to our solar system, and partly assembled from material that originally formed around other stars entirely. The Oort Cloud, then, is not simply a leftover, a passive relic of planetary formation sitting unchanged at the edge of the solar system. It is the product of an active and complex history involving planetary scattering, stellar interactions, galactic tides, and possibly even the exchange of material between neighboring young star systems. It formed over hundreds of millions of years during the most dynamic period in our solar system's history, and it has been slowly evolving ever since, its population gradually depleted by the comets that fall inward and replenished, perhaps, by the occasional capture of passing interstellar objects. Chapter 12. Voyager and the Journey into Interstellar Space. In the late 1970s, a rare alignment of the outer planets created an opportunity that would not occur again for another 176 years. Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that a spacecraft launched from Earth could visit all four of them in a single continuous journey, using the gravity of each planet to accelerate toward the next. NASA recognized this opportunity and designed a mission to take advantage of it. The result was the Voyager program, 2 spacecraft that would go on to become the most distant human-made objects ever built, and the first to cross the boundary between our solar system and interstellar space. Voyager 1 and Voyager 2 were launched within weeks of each other in the summer of 1977. Voyager 2 launched first on August 20th, followed by Voyager 1 on September 5th. Despite launching second, Voyager 1 was placed on a faster trajectory and quickly overtook its twin. Both spacecraft carried identical scientific instruments designed to measure magnetic fields, charged particles, plasma, and low-energy cosmic rays, as well as cameras and other remote sensing equipment for studying the planets and their moons. They also carried something else, a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life and culture on Earth. Included on the remote possibility that the spacecraft might one day be encountered by another intelligent civilization. The planetary encounters were extraordinary. Voyager 1 flew past Jupiter in March 1979, returning detailed images of the planet's atmosphere, its swirling storm systems, and its moons. It discovered active volcanoes on Io, the first active volcanoes ever observed on a body other than Earth, and revealed Europa's smooth, cracked surface of ice as a potentially significant location for further study. Voyager 1 then flew past Saturn in November 1980, examining the planet's ring system in detail and conducting a close flyby of the moon Titan. That Titan flyby, which passed close to the moon's thick atmosphere, deflected Voyager 1 out of the plane of the solar system and onto its current trajectory, heading roughly in the direction of the constellation Ophiuchus. Voyager 2 followed a different path. After its Jupiter flyby in July 1979 and Saturn flyby in August 1981, it continued on to become the only spacecraft ever to visit Uranus in January 1986 and Neptune in August 1989. The Neptune flyby included a close pass of the moon Triton, which was found to have geysers of nitrogen gas erupting from its surface. Another unexpected discovery of active geological processes on a body far from the Sun's warmth. After the Neptune encounter, Voyager 2 was directed southward out of the plane of the solar system, traveling in a direction roughly opposite to Voyager 1. In the decades following the planetary encounters, both spacecraft continued outward through the Heliosphere, their instruments still functioning and transmitting data back to Earth across ever-increasing distances. The signal from Voyager 1, traveling at the speed of light, now takes more than 22 hours to reach Earth. The spacecraft is powered by radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. These generators have been slowly losing power since launch, and NASA engineers have had to carefully manage the spacecraft's power budget over the decades, selectively turning off instruments and heaters to keep the most critical systems functioning. As we discussed in earlier chapters, Voyager 1 crossed the Termination Shock in 2004 and the Heliopause in 2012, entering interstellar space and becoming the first human-made object to do so. Voyager 2 crossed the Heliopause in 2018. both spacecraft continue to send back data from beyond the Heliopause, providing direct measurements of the interstellar medium for the first time in history. The data has been scientifically invaluable, revealing details about the magnetic field, particle environment, and plasma conditions in the local interstellar medium that could not have been obtained any other way. What makes the Voyager story particularly remarkable is its longevity. These spacecraft were designed and built in the early 1970s, using technology that is almost unimaginably primitive by current standards. Their onboard computers have less processing power than a modern digital wristwatch. Their data transmission rates across billions of kilometers of space are a tiny fraction of the speed of a dial-up internet connection. And yet they continue to function, continue to transmit, and continue to expand human knowledge nearly 5 decades after their launch. They are, in the most literal sense, humanity's first steps into interstellar space. Small, fragile, machines carrying the imprint of a civilization that sent them outward into the unknown, with the best instruments it had at the time, and the hope that they would keep going. The Voyager spacecraft will not reach the Oort Cloud for hundreds of years, and they will not pass through it for tens of thousands of years. By the time they do, their power sources will long since have failed, and their transmitters will be silent. They will continue outward as dark, cold objects, small pieces of Earth drifting through interstellar space, carrying their golden records into a silence that may never be broken. But the data they sent back during their operational years has permanently changed our understanding of the outer solar system and the boundary between our home and the wider universe. Chapter 13. What lies between the stars? Beyond the Heliopause, beyond the reach of the solar wind, and far outside the gravitational dominance of any single star, lies a region that is easy to dismiss as simply empty. Interstellar space, the void between the stars. It sounds like nothing. A featureless absence stretching between one solar system and the next. But interstellar space is not nothing. It is a complex, structured, and dynamic environment with its own populations of particles, its own magnetic fields, its own chemistry, and its own slow but measurable processes. It is, in its own quiet way, one of the most interesting environments in the galaxy. The material that fills interstellar space is called the interstellar medium, and it is composed of gas and dust distributed unevenly across the galaxy. The gas is mostly hydrogen, with significant amounts of helium and smaller quantities of heavier elements. Some of this gas exists as neutral atoms, drifting slowly through space. Some exists as ions, atoms that have lost one or more electrons due to exposure to ultraviolet radiation from nearby stars. And some exist as molecules, pairs or groups of atoms bonded together in the cold, sheltered interiors of dense clouds, where conditions allow chemistry to proceed slowly over vast timescales. The density of the interstellar medium varies enormously from place to place. In some regions, particularly the dense molecular clouds where new stars are forming, the gas can be relatively concentrated, though still far thinner than the best vacuum achievable in any laboratory on Earth. In other regions, particularly the hot, tenuous bubbles blown out by supernova explosions, the density drops to almost nothing. The Sun currently sits within a region of relatively low-density interstellar gas, known as the local bubble. A large, irregularly shaped cavity in the interstellar medium, thought to have been carved out by a series of supernova explosions over the past few tens of millions of years. The low density of the gas in the local bubble is one reason the heliosphere is able to extend as far as it does. The external pressure pushing inward on the heliopause is relatively weak compared to what it might be in a denser region of the galaxy. Within the local bubble, the Sun is embedded in a slightly denser region called the local interstellar cloud, sometimes referred to as the local fluff. This cloud is a few light years across and is moving through space at a different velocity than the Sun, meaning that over time the Sun is slowly passing through it. The properties of the local interstellar cloud, its density, temperature, and magnetic field orientation, directly influence the shape and size of the heliosphere. If the Sun were to move into a significantly denser region of the interstellar medium, the increased external pressure would compress the heliosphere, pushing the heliopause closer to the Sun and potentially reducing the degree of protection it provides against cosmic rays. The interstellar medium also contains dust, tiny solid particles typically less than a micrometer in size, composed of silicates, carbonaceous material, and various ices. Interstellar dust is responsible for the dark lanes visible in photographs of the Milky Way, where dense clouds of dust absorb and scatter the light of stars behind them. But dust is more than just an obstacle to observation. It plays a crucial role in interstellar chemistry, providing surfaces on which molecules can form and accumulate. Complex organic molecules, including amino acids and other compounds relevant to biology, have been detected in interstellar clouds, suggesting that the raw chemical ingredients for life are not unique to planetary surfaces, but are distributed widely throughout the galaxy. Interstellar space is also threaded with magnetic fields. These fields are weak by terrestrial standards, far weaker than a common refrigerator, magnet. But they extend across enormous distances and play an important role in shaping the structure of the interstellar medium. They influence the paths of charged particles moving through space, contribute to the dynamics of molecular clouds, and interact with the magnetic field of the heliosphere at the heliopause. The orientation and strength of the local interstellar magnetic field was one of the surprises revealed by the Voyager crossings. It did not align with predictions based on earlier observations, suggesting that the Sun's immediate interstellar neighborhood has a more complex magnetic structure than had been assumed. Cosmic rays fill interstellar space as well. These are not rays in the traditional sense, but rather high-energy particles, mostly protons and atomic nuclei, accelerated to near the speed of light by energetic events such as supernova explosions and the jets of active galactic nuclei. Cosmic rays travel through the galaxy in curving paths, deflected by magnetic fields, and they permeate the interstellar medium in all directions. The heliosphere shields the inner solar system from a significant fraction of these particles, but beyond the heliopause, they are present at their full galactic intensity. Both Voyager spacecraft detected a sharp increase in cosmic ray flux when they crossed the heliopause, confirming that the heliosphere does indeed provide meaningful protection against this form of radiation. The space between the stars, then, is not a void. It is a thin but real medium, magnetized, chemically active, and continuously shaped by the energy released by stars across the galaxy. It is the environment through which the Sun moves on its long journey around the galactic center, the medium into which the Voyager spacecraft are slowly traveling, and the context within which the Oort Cloud exists, not in isolation, but as the outermost layer of a solar system embedded in the broader fabric of the Milky Way. Chapter 14. The Edge of Everything We Know. We have traveled a long way tonight. We began at the boundary of the familiar solar system, just beyond the orbit of Neptune, and we have moved outward through layer after layer of increasingly remote territory, through the heliosphere and its boundaries, through the Kuiper Belt and the scattered disk, through the vast reaches of the Oort Cloud and into the interstellar medium itself. Now, in this final chapter, it seems right to pause and consider what all of this means, not just scientifically, but in the broader sense of what it tells us about our place in the universe and the nature of the knowledge we have assembled. The first thing worth acknowledging is how much of what we have discussed tonight is inferred, rather than directly observed. The Oort Cloud has never been seen. No telescope has resolved an individual object within it. No spacecraft has visited it. Its existence is deduced from the behavior of comets, from the directions they come from, the shapes of their orbits, and the energies with which they arrive. The scattered disk is known primarily through the objects we have detected at its inner edge, with its outer regions largely unexplored. The interstellar medium beyond the Heliopause has been sampled directly only at 2 points, by 2 aging spacecraft traveling in specific directions. Our picture of the outer solar system is real, but it is assembled from fragmentary evidence, interpreted through theoretical models that are themselves constantly being revised. This is not a weakness of science. It is how science works at its frontier. The history of astronomy is largely a history of inferring the existence of things before we can see them directly, predicting Neptune's position from perturbations in Uranus's orbit before anyone had pointed a telescope at it, detecting the presence of black holes from the behavior of nearby gas and stars before any direct image was possible, mapping the structure of the Milky Way from the distribution of radio emissions before any spacecraft could ever leave it. The Oort Cloud fits comfortably into this tradition. It is a prediction supported by evidence, and the evidence grows stronger as our observations improve. What lies beyond the Oort Cloud? In one sense, the answer is straightforward: interstellar space, and then, eventually, other star systems. Proxima Centauri, the nearest known star to the Sun, lies about 4¼ light-years away. At the outer edge of the Oort Cloud, roughly 1 to 2 light-years from the Sun, we are already a significant fraction of the way there. If Proxima Centauri has its own equivalent of an Oort Cloud, and there is no reason to think it does not, then the outer edges of our solar system and the outer edges of its nearest neighbor may actually overlap or come very close to doing so. The boundary between one star's gravitational domain and another's is not a clean line. It is a gradual transition, a region where the gravitational influences of 2 stars are roughly comparable, and objects might, over very long timescales, drift from one system to the other. There is a concept in astronomy called the Heliosphere, the region around a celestial body within which its gravity dominates over the tidal influence of a more massive body it is orbiting. For the Sun, moving through the gravitational environment of the Milky Way, the Heliosphere extends to roughly 2 light-years. The outer Oort Cloud sits right at this boundary. Objects at the very outermost edge of the Oort Cloud are only barely gravitationally bound to the Sun. A sufficiently close stellar encounter, or a particularly strong galactic tidal perturbation, could strip them away entirely, sending them into interstellar space as free-floating objects unbound to any star. This stripping process has almost certainly happened throughout the Sun's history, as the Sun has traveled around the galactic center over the past 4.5 billion years, completing roughly 20 full orbits in that time. It has passed through regions of varying stellar density, encountered molecular clouds, and experienced the slow but cumulative influence of the galactic tide. Each of these encounters has gradually eroded the outermost population of the Oort Cloud, releasing objects into interstellar space. At the same time, the Sun may have captured objects from other passing stars, adding new members to the Oort Cloud from external sources. The Oort Cloud is not a static structure. It is in slow, continuous exchange with the galaxy around it. The detection of interstellar objects passing through our solar system has added a vivid dimension to this picture. In 2017, astronomers detected an object designated 1I/Oumuamua, the first confirmed interstellar visitor to our solar system. It was moving too fast to be bound to the Sun's gravity, and its trajectory indicated it had arrived from interstellar space. Its unusual shape, apparently highly elongated, possibly flat, and its unexpected acceleration as it moved away from the Sun generated considerable scientific discussion and have not been fully explained. In 2019, a second interstellar object, 2I/Borisov, was detected. Unlike Oumuamua, Borisov looked much more like a conventional comet, with a visible coma and a composition broadly similar to comets from our own solar system. These detections confirmed that interstellar objects pass through our solar system regularly and suggested that the exchange of material between star systems, including the kind of material that might carry the chemical precursors of life, is a normal and ongoing process in the galaxy. We stand, then, at a remarkable moment in the history of our understanding of the solar system. Within living memory, the region beyond Neptune was largely a blank. The Kuiper Belt was a theoretical prediction. The first Kuiper Belt object beyond Pluto had not yet been found. The Voyager spacecraft had not yet crossed the Termination Shock, let alone the Heliopause. Pluto had never been seen as anything more than a point of light. Interstellar visitors had never been detected. All of that has changed within a few decades, and the pace of discovery shows no sign of slowing. The edge of our solar system is not a fixed destination. It is a shifting boundary between what we know and what we do not, between the domain of our Sun and the immensity of the galaxy beyond. Tonight we have traced that boundary as best we can, with the knowledge and observations available to us. We have moved outward from the familiar to the remote, from the well-mapped to the barely glimpsed, from the scale of planets to the scale of light years. And at the end of that journey, the universe does not feel smaller. It feels, if anything, larger and more intricate than it did at the start. The solar system extends far beyond what most people picture when they imagine it. It reaches into the darkness for distances that take light itself more than a year to cross. It contains trillions of objects we have never seen and may never see directly. It sits embedded in an interstellar medium that is itself part of a galaxy containing hundreds of billions of stars, each with its own system of planets, moons, and perhaps its own vast cloud of ancient ice at its outermost edge. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.